Good morning, everyone. Welcome to our first roundtable discussion. So the format this morning is going to be, well, we set a theme. We're going to have 3 themes for future directions. We called it big questions, but in reality, we have posed some questions on the future directions of the field since we have invited all you young people to participate. So first, we're going to hear from our panelists what they think on the questions we pose. And then we are going to hear from all of you, passing the microphone around the room. So you probably already know our panelists. Some of them, not all of them, have given their talk yet. I think Andrea is tomorrow morning. But yes, so they are not seated in the order that you see up there. We have Daniel Berg, Andrea Bracco, Emma Curtis-Lake, Simon Glover, Adeline Payment, and we will discuss future directions in observations, in simulations, and in data analysis. So as I think things progress, I would start with future telescopes and instruments, just because I think this is where our new science almost always begins, with discoveries from observations. So the first question that I have put up there is, what future telescopes or instruments you think would bring the most to our field? And maybe question 3 should go before that. I don't know what you think about upgrades and things we can do, actually new ways to use the existing telescopes or ways to use them better to learn about the ISM. So I don't know who would like to start with this. Yeah. You have the microphone there, whoever would like to start with comments. No.
Can you hear me? Can you hear me? Okay. Yeah, so hi, everybody. Good morning. I'm Andrea Bracco, so I will talk tomorrow morning. I mean, so today maybe there will be some spoiler. To complement the question you raised, I'd like to have a step back and say, sure, you know, that telescopes should be driven by scientific questions somehow. So it's really what kind of scientific questions you want to address with the telescopes. You build a telescope to address questions, and
yeah, then you find new ones.
The opposite. To my opinion, and also because it's the topic I'm working on, galactic magnetism. I mean, magnetism in general will be. So interstellar magnetism, but also in galaxy clusters, at large scales in the universe, will be revolutionized in the future decades. And this is mostly thanks to the development in radio telescopes. And that would be really a game changer, not because, I mean, we are very lucky to live in this time frame. So to me, this is really important. Magnetism that has been for long, and you know, because you work on modeling magnetic fields, but it's always been a challenge to confront models and data.
But what would be the frontier then, in terms of what we already have and what
sensitivity,
what we need?
There will be a jump in sensitivity, orders of magnitude, and that would help having, you know, sampling magnetic fields in different environments. And so we have statistical sample of data.
You mean the SKA, right?
Not only SKA. I mean, also in the northern hemisphere, you have upgrades of telescopes like LOFAR that will jump in sensitivity of an order of magnitude. There are telescopes like NanoFar that are very sensitive. Of course, you pay a trade-off between sensitivity and angular resolution, as always, but eventually putting pieces together the data will be available. Managing the large data set that will come will be a challenge. And so I can see that there is another point.
There is another point on the data storage and processing and what we can learn about the data with
and multi-wavelength. So this, people address some breakthrough in other frequency bands. Yes, the UV was mentioned. At least I listened to the talk. The infrared, of course. Now there is Phoenix that started. There is another infrared telescope that is incredible capabilities in doing both continuum and spectroscopy. And so putting multi-wavelength for studying ISM would be very valuable. And this is the first time we can do such multi-wavelength studies with high sensitive telescopes and with a lot of data. So again, this is very interesting, but then handling all this data, this is a challenge for the community. And to address the question you raise, how to use existing telescopes, actually, from my own experience, it's not just about upgrading or using existing telescopes. There is a lot of archival data. And, proposals are made for specific objects, possibly, or specific projects. But eventually, data may collect other science cases that the original principal investigators didn't think of. And so myself, for instance, I managed to produce some works on archival data of a few years back. And, this is very, I think there is a lot that is stored in the archives. And so you shouldn't forget that there is this kind of archival data present. Okay. And so again, it's a problem of management of data, how you store data, how you make the data accessible to the community, somehow friendly, usable.
I agree. And I also think that people, when they plan their large programs and their, especially large programs, and they should take care to make the data usable in the future and not just hoard it. But please, Pastor Daniel.
So I completely agree with multi-wavelength data, and I hope I expressed that to you yesterday. I think, in addition to what Andre was just saying, I'm worried about the X-ray future as well, like if we're going to have any X-ray detectors to go with things. And I think spatial resolution in general. So when you think of things like Chandra, maybe you're getting 1 to 5 arcsecond resolution. That's not great to understand your sources. I obviously really want a UV IFU in space in the future. I want us to have simultaneous spatial resolution across all things. And, I've been working on a NASA science case for the Habitable Worlds Observatory for this, of like, that is what will really revolutionize our understanding of like the ultraviolet, where we get the ionizing sources at the same time that we get the absorption along the line of sight, at the same time that we get the ionizing gas emission. Like all these things that affect each other come in the same place, and we could spatially resolve them would be really, really amazing. And then in terms of like, for nebular astrophysics, I personally think like all the low-hanging fruit has been done. And so we can do upgrades to our existing facilities. And one of the things is there aren't a lot of telescopes that have great, what I would call like moderate resolution spectrographs, right? So like you can get like 1 to 2,000. You can go get 100,000 for the planet people or stellar people. But like, we need more like R of 10,000 spectrographs to like do kinematics, but still be able to detect things that I think would be really, really useful. I'm really excited for Blue Muse, right? Like getting all these, as much coverage and sensitivity and spatial resolution as possible. So I think either going more spatially or more resolution in spectra in terms of like velocity resolution will be really helpful for understanding the different components and piecing back what's all going into the big picture we're seeing.
So what do you think would be, what do you think are the challenges in proposing a new X-ray observatory, a new UV observatory.
Yeah, funding. Like I'm sure, you know, I obviously have a very US perspective because that's where I'm from, but like we always talk about like the great observatories, right? Like we had 4 major telescopes in the sky at the same time, you know, doing gamma rays, X-rays, Hubble UV optical, right? And an infrared telescope all at the same time, major flagship missions. And, you know, I know Europe had like similar facilities. So like now we're at the point where we're building these giant things where like we can do one, right? Like one every 20 years. And that's not the same thing as having everything at once where we can learn together and make advances at the same time along similar axes. Like that's, and so I think it's going to take like cross-country world efforts to like build these things and make them come to fruition. It's the funding is so hard.
Is it a lack of funding, or is it that things have become more expensive to build?
I think both. I mean, if you look back at like what things were in those days dollars, like things were expensive, and technology's come a long way. It's not like we just have to build. It's not like things are like, okay, we just need it to be 100 times bigger, right? Like I know a lot about like UV detectors have gotten so much more sensitive. The UVEX telescope that I'm a part of, it is a 45 centimeter mirror, and it's going to be 10 times more sensitive than Hubble.
Wow.
So no, not necessarily. That's a medium class probe. It's only $300 million. As opposed to JWST is like, you know, billions, right? Like, so yeah, we can do it.
Someone else has a comment? Yeah.
Yeah, I mean, I think if you're imagining future big observatories like the X-ray or whatever, it's important to find a big community to support those. I mean, JWST has been absolutely awesome for doing nearby Galaxy ISM science, but if we just pitched it on that basis, it would never have happened. I mean, JWST happened because lots of people in lots of different areas of astronomy wanted it. And I think that that's going to hold for any of these big missions we might want to do for ISM science. You have to find other things to do with it, which I think for the X-rays is easy enough. But yeah,
We should invite them the next time. Emma, Adeline, you have a comment?
I'll take us back to maybe a lot of the low-hanging fruit is already there, but at high redshift JWST, we are still only getting started and we can use it better. So for example, if you want spatially resolved, you go after one galaxy at a time or something with NearSpec, or you have to sit with GISM, and that's hard. People are trying slit stepping programs with NearSpec, so that's like a multi-IFU, but really hard. And so there needs to be a lot of effort in the reduction of that and making that work. Other people are doing things where you take the multi-object spectrograph and you shut the shutters on the really bright things. So that's like a more sensitive GISM than any of the other ones. So, you know, there's still innovation to be done there with how we can better use our current telescopes to get what we need. And I do think we still need, at high redshift, larger samples going to lower luminosities to really get to grips with things.
So yeah, you want to make a final comment or?
Yes, I can bounce on what you were saying about using archival data, but that works also for the new surveys. The large amount of data needs some help to process, because you cannot, if you want to do a longitudinal study, large statistics, and you want to pick objects by eye, one by one, and fit things semi-manually, you're not going to achieve this large search through the archival data and through the large data sets. So I think it's also important to consider developing some purpose design automatic method for analyzing all this data, and to collaborate with computer scientists and data scientists to design these methods so that they are really suited for the type of data you're looking into and for the type of signals you're looking for. I think that comes together with building bigger instruments. because bigger data sets don't mean that you automatically get information out of it. You really need to dig through it.
Oh, this is an issue that we will discuss in detail. You raise an excellent point. It's something that is, yeah, it's in the next slides for the data processing, but it's actually, it is the central point of that discussion. So thanks for preparing that discussion. It is very, very important. Maybe before we move on, we can go around the room and hear comments or questions from everyone.
So you've been speaking about spectroscopy, importance of spectroscopy, which I think we all agree. But then spectroscopy, high resolution spectroscopy comes with the price of sensitivity. And so on the other hand, we want statistics. So we want to get instruments that are more sensitive to be able to do a large sensitivity, a large amount of data. And you said also that we need multi-wavelengths. Should we try to coordinate so that because we don't cover the full sky at all those frequencies, so should we coordinate so that better, so that we ensure that we target the same object at all wavelengths?
I have a quick question. What do you mean? Like, what statistics are you wanting? Because, like, for instance, if I think like, okay, the SDSS did millions of galaxies. DESI is going deeper and also now doing millions of galaxies. So, like, what specifically are you looking for more statistics on?
Yes, but those ones are not spectroscopy. Are they?
Yeah.
At which spectral resolution?
They're all R of 2000.
Okay, so then, but in the, for instance, in the millimeter on the far infrared, you won't get this.
Yeah.
You won't get millions of objects, not, well, hopefully sometimes, but
Right.
not now.
So you're saying we should combine a little bit higher resolution with statistics?
Yeah.
Okay.
We'll have Jackie. So first.
Oh, hello. This is
I don't
super
know.
interesting stuff. This question might be a bit beyond the scope of what you know about, but through what avenue do we do these international collaborations and propose telescopes? I guess how do we actually get the great observatories? Like how do we collaborate? Like, I guess I'm talking like kind of very fundamental, not like how do we unite the world, but like what is the avenue currently for doing those international collaborations and proposing and developing new telescopes?
Well, I'm sure other people hopefully can add on more, but I can say, like, on a simple level, like, let's say you're working on a project with NASA, you can subcontract an instrument or a different part from a different country, like get people to buy in all on the same thing. Or we can, as a community, say we're going to try to have, Japan do the next X-ray telescope, and we're going to try to have, Europe do the next, whatever big IFU, and we're going to have the US do, we could do it that way. But otherwise, it's like very business. There's subcontracts, and it's what each country wants to financially contribute and bring to that project. So it's like very formal that way.
I want to make 2 points. Starting on now.
You should move your hand.
No.
On the Planck satellite, and Planck satellite was a long journey. I was the lucky one that came, and basically I was the lucky one who analyzed the data, but that was the result of 30 years, 20 years, 30 years of work behind. And SKA now is the same. It's a journey that started 35 years ago. So when you ask what's the current status, well, you know, the telescopes that some of the telescopes we're seeing now are actually the result of a long-standing work behind.
Sorry, I guess the question is more something.
But
now, if I want an X-ray telescope, who do I talk to?
Yeah.
Like, do
So
we all
generally-
gather and call NASA up and say, "Would like an
generally,
X-ray telescope"?
space agencies, for instance, they open calls for
Yeah.
proposals.
Yeah.
And so if you have an idea, you build up community around yourself, and then of course you need support, and so you build a larger community. Eventually, you need to write a proposal, and then go through different selection steps. So I don't know if there is someone from
Simon wanted to say something.
Just going to expand on that a bit. I mean, ESA has a regular program for developing new small, medium, and large class missions. Small rather more frequently than the other ones, obviously, because they're cheaper. So you can put in a proposal to one of these, and lots of other teams will put in competing proposals, and then they will down select to a smaller number for more detailed study and eventually decide on one mission. So I think NASA does something similar, but I'm less familiar with exactly how NASA do it. But yeah, so that in practical terms is how you do it. You put together a team, you show that there is good science to be done with your proposed telescope, you show that it can be done with current or reasonably foreseeable technology, and you try and make it more compelling than the competition.
Jérôme, you have something on this? Okay, and then we go to Jackie's comment, or do you have something on this subject too?
Yeah, on this subject.
Yeah, and then we hear from Jérôme.
Well, first to share the information. So ESA has a great set of program in terms of multi-wavelengths. So Theseus is a gamma ray telescope still on the table, and New Athena is a big X-ray. It's also quite possible. And then on top of that, something not mentioned is far infrared is, I think, the undiscovered area. So if you want to go even very high redshift, beyond redshift 14, you have to go to even redder wavelengths. And Prima, for example, is looking good.
And it does have a polarimeter.
Also competing with an X-ray telescope though, right now.
X-ray and far infrared, yes.
Yeah, and then to comment, it's, in reality, I think it's very difficult to get a telescope if you say I want to have now. But all of these projects so far takes 10 or 20 or even more. So multi-object spectrograph have been planned long time with higher resolution. We've already online in the Northern Hemisphere. Foremost is coming in the South. Both of them have 20,000 spatial resolution with thousands of fibers. So these statistics and quality is coming. Even beyond community is thinking. So WST is a European-led mission. So we plan to build a new telescope with a higher resolution, even 40,000 spatial resolution, plus IFU, maybe coupled, but that's planned for 2040. Look, I was asked to lead some of the science team. I looked at my age. Am I there? But we have to contribute. It's a long-term mission. You also think I may not be in the community, but if you lost interest, these things do not happen. So we have to think, unfortunately, about the future, and then people have to contribute for the future.
And what a wonderful legacy also.
If I can make one quick comment before I forget. Right now, HWO has a lot of these science case development documents that have been put out. They're on the archive, and then they're soon going to ask for additional scientific community to sign on to these documents so that NASA knows which science cases the community is most interested in. And again, the exoplanet people are so much better and more organized than we are at these sorts of things. And so HWO, remember, is going to be UV, optical, and maybe some infrared. And so you should look and sign on. All you have to do is literally sign your name to these things, right? So it takes time for you to look through them, which ones interest you. They're only, they're these short things, and just put your name on them if they're important to you and tell your friends to do the same, because that'll help us make sure that those scientific capabilities happen in the future for at least this NASA next flagship mission.
No?
Yes, so it seems to me that if we want new telescopes in the next 20, we'll need to speak about science, but also we need to speak with instrumentalists.
Yeah.
Because you don't sell an instrument, you're selling an instrument only if you can prove that it's reasonable, you can do it. And breakthrough in sensitivity or whatever need technology, okay? And it's never given. So, and it seems to me today, astrophysicists, the community is too divided into instrumentalist or science or data analyst or whatever, because we need lots of specializations, but we need to talk together in order to get the new generation of instruments being built.
It's a very good idea also for the next workshops to have instrumentation discussions as well. Yeah.
Yeah, I feel like until now we have been mostly discussing about imaging and spectroscopy, but how about time resolved imaging or spectroscopy? How is that going to change studies of the ISM? Do we have any inputs to give there, maybe with the Vera Rubin and upcoming scopes?
I was just to say, one thing I'm really excited about is the UVEX telescope is going to launch in 2030. Again, this medium-sized UV telescope. We're going to image the entire sky very rapidly on short time scales. We're going to go back to different parts, hours to days, but we also have rapid follow-up anywhere on the sky within 6 hours, which is really rapid for a space telescope. Right now, you're lucky if you can get to something in 1 or 2 days with existing space telescopes. So we're really exciting that if you have something that goes off, something you want to follow up rapidly and follow for multiple time things, within 6 hours, we can get to it and start tracing it. So we have a specific science case for time domain with UVEX that we're really excited about if you like ultraviolet, higher energy time domain.
Well, on the low energy side, so in the radio, SK will, at least for what I know, will have high capabilities in following up transients. But also, if you want time variability sources like pulses, for instance, with the radio, you will be for ISM studies, it will be very valuable. Basically, for pulses, you can estimate their distance through parallaxes. If you follow them for a while, you can find their distance. You can measure the rotation measure that you may have heard last week. So you can measure dispersion measures. So you can have information about electron density along the line of sight, and you can know magnetic fields along the line of sight. And with new facilities, we'll have a large sampling of sources around across the sky, and so this would be very valuable.
Do they do this for ISM or do they do this for gravitational waves?
Sorry, I didn't.
Do they do this for gravitational waves or for yeah? I think that we are equal to gravitational waves for this.
Yeah, but I'm not really an expert on that.
Yeah. Other comments or questions on the subject of
Just other ideas for important telescopes. So when we try to do multi-wavelength, the bottleneck in terms of angular resolution is often the far infrared, because we can only observe it from space. And so I'm enthusiastic about Prima, but the beam of Prima is really a bummer. And on the other hand, I don't think that engineers will be able to go on showing off by making fancy foldable mirrors that we can shove into rockets. So I think the next step, I forgot we were talking about it at dinner the other time, is really to have a far infrared interferometer in space to really try to catch up the angular resolution at other wavelengths.
Well, why not? You always have to remember that with interferometers, the limit is the sensitivity. Okay, so it's in order to be able to use correctly an interferometer, you need lots of collecting area.
So as Andrea said, all these telescopes, both Brown and space telescopes, take a lot of time. And junior scientists do not have the time. Or at
Senior
least
scientists
from my
have
point of
less
yeah,
time.
scientists, like we have to do the science. We cannot focus on a future idea that may happen or not. How should we approach these projects? It's
I
very
think
helpful.
that's a personal choice, right?
I think
don't
this
know.
is also a matter for the roundtable on Thursday.
Yes, I
But
think that, yeah.
I read the title of the roundtable is something that nobody will teach you about research.
Yes, yeah. So
we can discuss about
but
that.
I would say that if you have a calling or an idea, if you want to go for this, you go for this. It's fine to not want to. It's fine to not want to put the time. But if younger people don't do it, who will do it? The time to have a vision and invest in that vision is when you are most active. Of course, experience and being more senior will be useful, and you have everyone on board. You don't expect a PhD student to lead a space mission, but you need people on board, and you need them enthusiastic and with ideas, because you're the ones who are going to use it. I mean, if you see something that's going to fly 2040, yes, yeah, you do invest in the next generation, but the protagonist should also be the next generation, I guess. In terms of vision and ideas, not necessarily in terms of investing all your time on this.
Yeah, I was going to say, you may not be able to invest a lot of time in it in your PhD, but 3 or 4 years in the future, if you want to continue in research, is when you want to start showing people that you're thinking about it. So if you are put into the opportunity where you get to hear about these ideas and these future telescopes, then log them. Also, you can be signing up to these things to express your interest. Maybe your supervisor is working on a science case and you can just contribute a plot, which would take you a couple of days. This would be something that would raise your awareness of these things without having to invest all your time. So you may not be the people suggesting the next telescope, but I would suggest that raising your awareness to the possibilities is worthwhile even in your PhD.
Yeah, so it's just to add something about this is that we need people working for and developing instruments, scientists who are involved in this, because as Jerome said, we need to be at the same time astronomers to know the science cases, but also to talk to engineers to optimize everything, to develop what we need, and to push the instruments to obtain what we want. As Emma said, for the GWST, we are not yet at the limits of what we can do, and we need to do that.
I think this is, yeah, so let's have another comment and then we can start moving on to.
Yes, I think many people were like advocating for like the large missions, and I agree in the sense that these will be the missions that break stuff and really drive allow for like huge steps. But I think it's also important to emphasize that the foundation for this mission are always way larger missions, like to explore technologies and so on like the 50 million euro level or something like this. And I think it's really important to also have an eye on them and acknowledge that, because they also take time, not as much time as the flagships mission, but they in the end allow really to write like the interesting sentences in the proposal for the larger ones. And I think there are plenty of these missions upcoming. These are balloon missions when it comes to like the far infrared, and also detector development studies for like the X-ray missions, which make it possible to allow to really aim big.
So I would suggest, unless there is a interesting or another different point to bring up, we can move on to the other direction of the frontier, which I find is a little bit lagging personally. I don't know why, but So I feel for a long time that we are reaching the limits of what our codes can do. And I think our codes are our algorithms are the limits to numerical simulations, not the infrastructure. The infrastructure is going forward very, very fast. We're hitting the exascale limit now, but our codes are not very scalable. They're not very young. As you saw from Simon's presentation, we still have many issues to resolve. So I think that I think it's useful and actually necessary to discuss what will be the what will bring us out of this. What do we need to do in different directions to improve and to make the most of the infrastructure and to keep up with the observational efforts that are like really pushing boundaries. So I don't know, Simon, if you have comments on this.
Yeah, I mean, I just want to start by recapitulating the point I made at the end of my talk on Thursday. We need to decide what to do about GPUs. The biggest machines in the future will be GPU based. At the moment, the big hydro codes that most of us use do not run on GPUs, or maybe have a few parts that run on GPUs, which doesn't really give you the benefit of that acceleration. So do we rewrite everything? Do we try and selectively port costly things to the GPUs? It's not clear to me what the best strategy is.
And it is a very steep learning curve to program something on a GPU. So I've been programming for quite a while, but it is challenging because each architecture has its own peculiarity. So you have to train for it. And no one has time to train, right? So we need people probably who are very, very interested in this, and we would be doing it anyway, to invest in astrophysics. So, and they're usually better paid somewhere else. So this is a big problem. I don't know if it's a problem also in instrumentation, but the software engineers who would be the best to do this don't go to astrophysics. They go to a higher paying job. Yeah. So
yeah, I mean, I think the other problem is it's difficult to like go to a PhD student and say, look, I want you for your project to rewrite this code to get it to run on the GPU, and you won't get to do any science because it will take you 3 or 4 years of your PhD to do this.
And you may fail and not publish anything.
Because you haven't published anything, you won't get a job afterwards. Yeah. So yeah, that doesn't work. So how do we find the people to do this without kind of some support from within the community to actually do this?
I partly disagree with you. Okay, because if you're looking at Ramses, it's been one person that took the jobs one day, very bright, and he built it. Okay, so you should not say to young people, don't take risk.
No, it's not that. It's that I cannot give it as a PhD project. It's too risky. You cannot put that on someone. I've seen people completely ruin their mental health on this.
Let's say it's the other way around.
Not everyone is Roman or Volker.
Not everyone, but let's try to bring to the subject people who are very bright and wants to do this. Okay.
No, yeah.
Even PhD, I would say, even at PhD level.
I agree with you, but you have to find someone in the golden point where they are super interested in doing astrophysics and they are trained in computer engineering or very interested in that. And I think it's a very rare occurrence.
I have a general comment, not only related to this specific issue, about we should foresee some specific path for some people that dedicate their time to these tasks that are useful for the community. I'm thinking about the case of Gaia. For instance, we had in my institute, but I think also other institutes in other countries, postdoc fully dedicated to preparing the mission, to preparing the tool for analyzing the data. And they spent all their time hardly working on that. They are now out of astrophysics because they were not competitive at all in, a public competition for permanent position that I mean, is the ending point for people starting the PhD. I don't believe that they are happy ending somewhere else because they want to do science. And I think at the level of politics, we should press to have such figure recognized for their work. So it is for preparation of space mission, for preparation of big instrumentation from Earth, and also for these tools for heavy computation. But this is up to us senior people, actually. This is our task.
Jackie, do you have comments on this?
Yeah, just go back to Simon's point. So the UK big supercomputer called Dirac is most certainly go to GPU. And then the question is really happening. How many people would like to keep CPU? If anyone wants to use existing code, maybe it's really the time to shout up.
I think that in Germany also they are proposing that the next 2 years, if you don't include GPU assisted at least codes in your proposals, they will not go through. So because it's also an issue of carbon footprint. We are leading the carbon footprint of the community. Each time we run a simulation is like taking a flight. So, you know, you see a big ERC project with tens of millions of CPU hours, it's as if you were flying every day here and there. So it's a big, big investment, and we feel it, and we need to optimize. So I don't know how it's going to move forward. GPUs is definitely the most obvious way.
That coupled to my second point, which is during the argument, okay, if you want to go to GPU, we need a person to program, to convert our code into GPU. And then there is a possibility to ask funding to support people from even computational science properly trained with high performance computing. And that's also happening at the same time. So that's, you know, we get the people to convert the code or we keep CPU. And I don't know which is a better way.
I think we need both directions. I think we need to have a direction that goes towards algorithm development, actually better software, and at the same time, algorithms that work better on a GPU. So I have the feeling that it will work better if we scrap everything and we restart from scratch for the coding. Rather than patching, well, of course, you have what you have. Sometimes you need to patch it, but our codes are, some of them are decades old. So they might need a refresh also in terms of algorithms and optimization. Yeah.
So I had a first point, which was I will say it again because it is a rephrasing, but it just saying that it's everywhere, supporting software developers in science, like the people that stick around, it's because they found some soft money or someone is supporting them. So if anyone is also someone with lots of soft money, then maybe they can support the local software developer. But also look in terms of like machine learning and how that is sort of coming up through. You see that they're being like students are being taught at undergraduate or master's level, coming through and, you know, have all the skills? Is it something where you can start to implement some courses with physics courses for GPU programming at an earlier level? They will come back through and be much faster than us. Like retraining us at this stage is, maybe you have to write the lecture course, but I don't know.
No, I think that it's going to be necessary. I think it's going to be necessary to find also lecturers to do that.
This is super interesting. And I feel like I'm new to the conversation about GPUs. Can you define more specifically the pros and cons of GPU versus CPU, and I guess ultimately the differences?
Okay. I mean, briefly, a GPU is really, it's optimized for doing vector operations. Is a simple way to think about it. So operating on large numbers of numbers simultaneously and doing the same operation to large numbers of bits of data simultaneously, because this is what you have to do when you're actually doing more fancy computer graphics. Also beyond vectors, there's more complicated things called textures, but I don't really understand those. But yeah, so it's basically an approach where you are massively parallel in each operation, but then you need to design your algorithms to work that way rather than sequentially going through a loop and doing a bunch of things each time through the loop. You actually have to make sure that you can make use of that parallelization. Also, many GPUs are just single precision. I think the majority just use single precision, which isn't always a good fit for what we want to do in astrophysics, but is because for displaying stuff on the screen, you generally only need single precision. Also, in the past, these things have been quite limited in terms of memory. I think this has changed a lot recently. So I think these days you are less limited in terms of memory, but you still have to pay a cost for transferring stuff from a CPU to a GPU or back again. So you also ideally need to put stuff on the GPU and do lots of computation there before taking stuff back to your CPU and communicating with other nodes. And if not, then you spend all of your time shuffling data backwards and forwards and you lose any benefit of the speed up. I think there's a comment at the back.
Just to add one little thing to the GPU thing, also, other than being specified for vector operations, also a GPU has thousands of cores with respect to CPUs, and that's also a thing. And going back to what was said before, the thing about the machine learning popping out so much to these days, also as like university courses or entire degrees, is that it's a subject that has been developed a lot during the last like 20 years. And like it comes a lot as a black box that needs to be used and not much to be developed. Like there's some development going on, but the way they teach you is a lot like a black box. Whether GPU development is not coming as a black box. Like you have to study the CUDA language and develop specifically for GPU, and it's something really hard. Like I've done something about it, and it's really hard, and it will take you 3 to 4 years, as they were saying before. Like.
And then you want to go into you teaching computer science.
So I also don't know much about GPUs and CPUs, but in theory, is it possible to rewrite all codes to have them run on GPUs, like for the codes you're working on? Or are there some limitations where you have codes that currently run on CPUs that are impossible to run on GPUs? In a perfect world.
Well, GPUs are Turing machines, so in theory, you can run anything on them. The question is, can you run things on them efficiently? It's the harder question to answer. I don't have a good answer to that.
So at least with Arepo, I know the thing is that, for example, the Voronoi tessellation you do is very non-trivial on GPU, while you can easily do that basically on a CPU. Whereas if you want to run like AMR codes or SPH codes, there's actually a relatively nice way of splitting up your computations such that your GPU can run them. So the thing is that a GPU has very many cores, but not that much RAM, at least in the past. And the CPU has basically little cores that can do like more operations are more capable. So that's why it's a bit hard to port existing codes, I think.
Thanks. I'd also like to note a point that Simon made earlier. If you port everything to a GPU between like transferring your data from the GPU and the CPU, if you put everything on the GPU, just thinking like, oh, a GPU is faster, it's more efficient, you're going to run into a bottleneck that you would with the CPU. You need to find a way to optimize both the GPU and the CPU. I know NVIDIA is actually offering free workshops as an intro to GPU and where it's going to be more efficient for your code. But we can't fall into the line of thinking that we can just put everything in the GPU and it'll be fine.
I think that people have tried that and it failed. And I think that when you use a single GPU, things are even like quite okay. But parallelizing multiple GPUs has been very unsuccessful so far. Very few codes have managed to do that. So I think it's really, really worth it investing in these workshops. And especially for younger people, I think it's an excellent opportunity. Some of them are completely funded. So you take some time maybe out of your PhD, a couple of weeks, and then you have some extra training if this is your interest.
I think the other issue related to this bottleneck is it often you don't get much benefit from just putting part of your code in the GPU unless you have a part which is utterly dominating your computational costs. So for instance, some n-body calculations where
Gravity or ray tracing.
Estimation for all of the stars in the globular cluster, that gravity calculation is such a dominant part of the cost. If you put that on a GPU, you really do get a big speed up. But for a lot of what we do, the hydro codes, where there's nothing that is so dominant, you just put part of it on the GPU, you don't really go any faster because then you're just going to be limited by the bottleneck. So it's not, you don't really get any benefit until you've done all of the work. It's not a case of like, oh, we just rewrite this bit and already get some speed up.
I mean, about the bottleneck is really not that much about software, but it's more architectural. Like you need a really hard development on the platform where the CPU and the GPU operates, because the thing about transferring the data from the CPU to the GPU, it's really the memory bandwidth and speed and transfer speed. So there's nothing you can really do to optimize this at a software level. And also about using the GPUs, in the end, you really want to put on GPU the really hard computations, because at the zero order, you're not gaining much performances for simple tasks. Like your CPU will take 3 milliseconds, your GPU will take 1 millisecond, you're not gaining much. Where you're gaining a lot of performances is for the hard tasks, where really a lot of cores which GPU have benefit from it.
So, I mean,
so just to comment a little bit on the bottleneck, the carbon footprint, I think that if we just start putting all the codes in GPUs, I seriously believe that we will raise the carbon footprint by a lot. Because first of all, the CPU, if you have a CPU running 100%, that might consume 80 watts from like a power supply, and then you have the new GPUs that they consume 600 watts. Then if we start running codes instead of 1 million cores of CPU, and we start running them in 10 GPUs, then the carbon footprint would elevate exponentially, I would say.
Not exactly, because if your code is 100 times faster.
Yeah, but GPU.
You have a 10 times more emissions per GPU. You reduce them to 10, you had 100 times the speed up, but that's not an exponential growth, I'm sorry. I don't know. I mean, I understand what you're saying, but the efficiency issue is really the matter here. So if you can run the same thing on something that, is more energy intensive, but is tens or hundreds of times more efficient, then it's worth the effort. That's why we're doing this.
Can we use existing instruments, for example, TensorFlow, to adapt them to our codes?
Sorry?
Can we use existing packages like TensorFlow, which you commonly use it for machine learning, to adapt it to Ramses or Aleppo and use it like a black box instead of developing these hardware things?
I think it's a different thing, right? So you mean approximating some processes with an emulator, or what do you mean? So
I don't know enough about what TensorFlow actually does to answer that
Yeah.
question.
yeah, I think that we're not very. Yes. Oh.
So it's kind of like a summary of what you've said, just to make sure I've understood it correctly. So to take full advantage of a GPU, you would have to run your full code on it, not just shuffle it around. And currently it's unsure if it would be faster and the result would be better if we rewrite our codes like that run on CPUs to GPUs, or we would just start from scratch. So no one really has an answer for that question mark.
I vote start from scratch, but just because people tried to do the existing codes on GPUs and have not been successful, because the point that was raised before, I don't agree that if you know that your architecture behaves a certain way, as a programmer, you can use that. So you know the limitation and you can optimize with this limitation in mind. If your architecture is limiting the communication, you will, as a programmer, not use communication. So you have to go to an algorithm, talk to mathematicians, talk to software engineers, and find the algorithms that take advantage of that and make it integrate that into the code. The way our codes are built now are very much based on communication. So there's constant exchange of information between the processes. So this will destroy, that's why it's not working actually, because you have to communicate fluxes, whatever positions all the time.
I think that the discussion is a bit pessimistic on GPUs. Okay,
Yeah.
It seems that it's very difficult. What I would like to say is that it's possible. Okay, it's possible in astrophysics and in MHD. For instance, there is Geoffroy Le Sur that has developed EDFix. That is a GPU code try to solve our problem. So not only trying but succeeding to solve our problem. So it's possible. Okay.
No, it's just that we need to invest in this direction, because if we have like one or two people trying to do it, it's going slow.
It's like Annabella said, we need to reward people who do the other also.
Yeah, exactly.
I may just be throwing a random comment in here because I just didn't know if we'd ever come back to anything else for this discussion. But I think that sometimes just from what already exists, observers need to be better at communicating what we need from the simulators, because we're limited by what we can observe, right? We only get what we can get from the universe, from our observations. They can put out whatever we ask them to. We're not very good at communicating and speaking to them directly so that we can match one-to-one with the simulations to our observations. And so that, like even as a junior observer or whatever you're doing, talk to all the people computing things, reach out to people that wrote a code or a paper and ask them if they can give you this other output or different things like that. Because even without expanding or redoing or converting, a lot of times there's things that exist that are just getting lost in communication that we could already do better now. And so I just wanted to make that point.
I think it's a valid point because we also need to reduce the number of simulations we do. So it's a simulation is not like I launch something to resimulate the universe exactly. It's an experiment. It has to be targeted. And I think many people forget, me included. Yeah.
So I can build on that, yeah. So in terms of some of the most exciting things that as an observer I'm seeing, it's developments in forward modeling onto the observational plane. And then it doesn't quite go in the direction of fewer simulations, but simulation-based inference. I'm also a statistical modeler.
Yeah.
Taking your simulations and your tunable parameters, varying them, comparing them to the observations and finding something that rather than just tuning them to fit to something at low redshift and seeing what happens, you can better match your simulations. You get a lot of detailed information. Unfortunately, it does push towards more simulations, and at the moment at lower resolution.
Yes, that is the motivation behind all of this, behind wanting to make the codes more efficient and more flexible, is exactly because you have a big parameter space to explore. So one simulation is not enough, one experiment is not enough. And we are hitting this this wall now because there's a lot of observational data to interpret. Yeah, absolutely.
I think we can also be cleverer about how we explore that parameter space. I mean, there's the tendency towards doing the most obvious thing, which is varying one parameter at a time. And actually, this is provably quite inefficient when you have a lot of parameters. And there are better strategies that you can use that mostly people in the field don't know about. So, I mean,
Last week we learned something about this, right?
Yeah. I mean, we need to learn from the people that do know how to do this efficiently and who know about things like simulation-based inference.
And just a final one to add, you're talking a lot about talking to people with different expertise. There's also AI and large language models that can help, right? So you can use them to your advantage where you can't find your expert. You can go and ask stupid questions. You don't always know that you're getting them right, but there are cleverer ways of using it. For example, taking a paper and say, explain this paper to me as if I'm a physicist, not I'm a mathematician. And so you can start to approach literature that might feel a bit too heavy to begin with, but start to understand the concepts at a level. So there are clever ways of using this when you don't have access to your expert that you need to transform your field.
So I would have a question, and it's, I mean, this is all nice, but how can we as a taxpayer-funded community compete against global mega corporations for like these bright minds that know how to program GPUs and even like get the GPUs for costs that you can write in a proposal? Because I think many of these efforts, I would love to see that, but of course, both like the price for like the people and for the infrastructure has risen really quickly now, and there's currently, at least, I don't think like an end in sight.
The same question can be asked for data scientists. There's a big issue at the moment for recruiting academics in the data science community because they all go for these big companies. The one who remains are the ones who are interested in science and want to do research in science in this data science field. So I think if you can interest people who are interested in science by proposing something that is not just a development job, but has some science for them as well, that's maybe a way to get people motivated for doing that. So it needs to be a win-win thing, science in physics and science in computer science together. That can be a good option to get brilliant minds doing this job.
I want to add on that, like, so at least in New York, I'm thinking of several people who have recently moved to companies like Google from developing software for astrophysics simply because they have families and the pay is much better. And why would they, like, they're passionate about astrophysics, but they can't compete simply with the pay we're offering. And that's not an easy solution, especially when we're funded by things like taxes. But maybe like one thing that we can all be better on is being sure to give recognition to the packages we're using and the people who develop those packages, like citing and acknowledging those accordingly. I've made like a big effort to go through, make sure I'm acknowledging the contributors of those packages, because I feel like sometimes it's a lot of time and it's a lot of effort to develop those, and then sometimes we can use those and make our code more efficient, and then kind of like forget to acknowledge the people that make that possible.
I was just going to also comment that the people that move to industry might still be interested in science. And in your grants, you can fund small contracts for those people. And their companies will often let you pay them for a month to do that work. So they keep their overall higher salary where they're happy, they get to contribute to science, you get their expertise, and it only costs you 1 month of expensive funding as opposed to trying to hire someone for 3 years or something like that. I'm not saying this is the perfect solution, but it's also, I know like when I advise postdocs and they're worried about going into industry, knowing that they could still contract or still keep connections and have those ties to science also helps them feel better as well. And so I know some people that do actually do this. People that do resolved photometry. Andy Dolphin works for IBM and he wrote Dolphote. He continues to advance Dolphote and write it for new platforms and to collaborate with people. He's the only person that knows how to do it well. So there are like ways to do that, just to throw that out there. And maybe that's how we should be funding it, is contracting short amounts from the best people that are in industry.
Yeah, just a little comment on that. Well, then I think also, the kind of the job system works in different countries can be an obstacle somehow. It's kind of, I'm not sure how much. I'm not sure how much European countries could allow such dedicated, like a month contract to.
You hire them as contractors.
Yeah, you can do that.
Yeah.
Like in your C.
Bunny, yeah. You hire external contractors, and projects usually allow for that.
Okay. Yeah, this is something that. Yeah, this is what I was wondering.
Yeah. Maybe this one.
So as a data scientist, but not a mathematician, yes, often people from astrophysics consider us as mathematicians, but truly, if you met some mathematicians, you will know that we are not mathematicians, really not. And we try to be comprehensive, actually, maybe if we don't. So yes, the question was how to take, so Adeline made a lot of work on trying to management the data, so she will talk about it, I guess, in 2 minutes. And also the other subject that I would like to discuss also is when I say how can we learn from the noise, it close to a remark from Jérôme, like how do you take into account the noise in your raw data? I mean, the systems that generate the data, you should take into account the noise and talk to the engineers who build the system so that you can have better information from all your system. And the simulation we already took, so now is a good time to, yes, it works. Adeline, maybe on the management of the, oh.
There's a lot to say.
When you work about all the data, when you try to convince people to participate to the science and help to manage the whole data and contribute to the classification of the data, maybe you can talk about this also.
Yes, the whole data analysis pipeline it requires lots of people involved usually. There are different aspects that need to be covered by different people. Of course, there's the data collection part. So all the instrumentation that was already talked about. But then once the data is collected, it depends really which information you're interested in within this data. If you want to explore the data without any exact idea what you're looking for, apart from something new, something surprising, you will have a different, you will analyze the data differently than if you are looking for something very specific. If you're looking for something very specific, that means you already have a definition of what you're looking for, and you need to provide this definition to your data analysis pipeline. And that's usually done through providing examples. So you need a lot of effort into analyzing manually some of your data to cover these examples so that you can then use them to train your methods into automating this analysis. While if you're exploring your data, well, that's there's sorts of things that I talked about last week. You will choose completely different methods. In any case, you need good expertise in choosing the algorithms you're going to use, in also managing all the data preparation. A lot of work goes into cleaning the data, making sure there's no artifacts that your human eye will automatically suppress, but that would completely confuse a machine. And this data cleaning process is usually very largely overlooked. It actually takes a lot of time and effort. And PhD students and postdocs are usually the ones who have to deal with it, and they have to take a lot of time of their PhD to do this. And this is not usually really acknowledged unless they can produce a nice, clean, curated data set that is going to be shared with the community so that it can be reused again and again, and maybe used as a standard benchmark to compare analysis methods. So this data preparation is one large task which people need to be aware of when they want to go to the machine learning methods, because they cannot usually be used straight away on new data. The data needs to be prepared quite extensively. So you have this data preparation, you have the example annotations. If you're doing supervised learning, you have the expertise that's needed for picking good algorithms and tuning them. And then you need also some expertise to interpret the results, because sometimes what comes out of the algorithms is not fully obvious to a human what it means. It can be difficult to interpret them either as sometimes people, I see some people unsure of whether what comes out of an algorithm is statistics. Is it a completely abstract score that doesn't have any physical meanings? What are the guarantees that do we have a way to understand if the output is correct or not? There's usually no guarantees with coming with these algorithms, so it requires a bit of expertise as well to understand the outputs and be able to include that in your own work. So all of this requires collaborating with quite a few people, both people who are experts in the data and people who are experts in the methods. And I didn't talk about the management of the sheer amount of data storage and sharing with the community, which is another large task and technical challenge. Maybe you are more familiar than me with that.
That building on that, all these different surveys run by different countries, different places are happening. Even there's a lot of imaging data that's coming online right now, right? Like we've gotten a lot of Euclid data that's happening. We've got Rubin starting to run. Roman's going to be launched next year. We have a lot of these like really big data sets that need to all be linked together with existing data sets, with all these other upcoming data sets. And so, because if you're, for instance, looking for, maybe you're just looking for unique things, but maybe you know you want to study some particular part of the sky or objects, they all need to be matched up. You need to be able, how do you take from all those extremely large data sets and extract your one object from all the different ones? How do we put these all together? And so this is obviously an ongoing problem. I know there are two, in the United States, there are two National Science Foundation AI centers that were funded last year, $20 million centers, and each of them are taking a different approach. One is doing, I think, more optical data, and the other one is doing like radio data. So I think it's optical infrared, and then the other one's doing radio data. And they're trying to build these more comprehensive ways to search and find and cross correlate all these different data sets to help astronomers use them specifically for astronomy. But are there other ongoing efforts? And
well, I can tell you the experience with the SKA. So the SKA will be a huge infrastructure itself. But then there will be another step, because the observatory itself won't deliver data to the community. You will be able to access the data through a specific architecture that is called SKA Regional Center Network. And specifically is a network of high performance computers around the world. And you as a user, you will access through one gateway. You will be completely blind where your data are stored. And all of that is under development, under discussion. So it's, I mean, I personally, I'm working as a project scientist in this structure, and it's a huge challenge. First of all, because you need to put countries to talk together. You know, it's a policymaker problem at first place, and then you need to understand how to. Are you moving data? Are you copying data? All these, and SKA is supposed to give like 700 petabytes per year. How do you handle that? So this is active discussions. And for instance, if you want to cross-correlate large radio surveys that you will have with an SKA with other surveys, it will be challenging, of course, because you will need to do that through these SRCnet, which is not, you know, then you need to face with other collaborations and understand how to access the data in different contexts. So this is an ongoing process, but it's challenging.
Eva?
I think I have heard from people, mostly like older people like me, and it has crossed my mind too, is that when you have to filter this data, because it has to be automatically filtered before it's stored, the raw data cannot be stored. It has to be somehow selected on the fly, right?
It will be, the data will be pre-processed.
Yeah.
From the observer. I'm just
yeah.
example
So,
of SKA.
for the example of SKA.
Yeah.
So
the data will be pre-processed.
Yes.
Then some compressed version of the data. So we are talking about interferometry. So the question is, are you having visibilities, or what kind of graded visibilities or average visibilities? And then on the SRCnet, there will be possibility. The SRCnet will have two goals. On one hand, it will need to assure the possibility to process the data again. So you will need to, you can reprocess the data.
So you have access to the raw visibility.
Not to the raw visibility, to the pre-processed ones. But then you will be able to continue and finalize your processing.
Okay.
And on second step, it will be to archive the data, access the data, and so on.
Yeah, on this, it's very important that us as a community has an idea of the kind of data we need, because SKA is trying to do wide field high angular, high spectroscopic resolutions, the time domain astronomy, to serve all those community. And of course, that's why we end up with 700 petabyte per year. But as a user in the interstellar medium, you're not, it's unclear that you need all those dimensions. And that's the same for all the science categories. So we need to think a lot about which of those parameters we're interested in, and whether where we really need the resolutions in order to reduce, because so SK is saying that it will deliver 700 petabytes per year in 2030. We are not ready to do this. We are working to do this, but we are not ready. So we need to think in ways to reduce this data set so we can take out the power of SK.
So not SK will be an observatory. So there are two kind of facilities, I would say, surveys and observatory. Observatories means that the telescope does specific programs, specific projects, whereas survey is just scanning the whole sky with specific features in the telescopes. So SK will be an observatory. So of course, each program will have different requirements. And just as a note, the computing power and the computing needs of your project will be included in the time allocation for your proposal. So you will need to estimate how much of the network time you will need to basically go from data to research.
Did it answer your question, John? Any other questions from the students? So, and with SKA, you will have a clear view of what are do you take into account, like, does it answer to one of those questions?
I think I agree with Jerome. We're not ready to answer any question, but we're clearly facing problems and challenges that will need to be addressed in 5 years' time, once the telescope should be at full run.
But those problems are from trying to draw more people or more technology, or
management for me. How you need to find a way to optimize the data that are coming from this huge facility in order to maximize the science you.
But how was the compression took into account when you stored the data? Like, what kind of compression? Do you make a partition of your data? Or?
Well, at first, what kind of data products are delivered from the telescope? So, as I was saying, do you need all visibilities? The raw visibilities won't be able to do that. So they will need to be compressed, averaged in time, or gridded. How would you grid your visibilities? And all these is under discussion. Nothing is settled yet. But the final goal is to have something that it will be a trade-off, of course. This is a facility that will observe from 50 megahertz up to 15 gigahertz, and so you cannot do everything at the best possibilities at once. So it's a trade-off between how you do good science, great science, but at the same time, the kind of products you can deliver to the community.
But do you plan to adapt the grid to this particular place?
Yeah, this is very important to
Number battery?
Yes, to think in science questions and what your science really needs about the data. Do you need, for instance, if you're looking at trying to look at enrichment, you may want to do time astronomy. But if you're looking into the ESM in galaxies, probably you don't need you're limited by sensitivity, and then you need to integrate long times on your data. And it's not at all the same way to store the data, those two different science cases. So it's very important to ask questions in a science way, knowing what kind of science question we are asking, and to think in advance. As you say, the computing power will be given, but it's not free. Okay, they have to pay for it. So not only the acquiring the data will be competitive, but in addition, you will have to compete to access the power of it. So you need to think what kind of how to be efficient in answering your questions. But that's the same question in my view that you're asking when we are discussing with data scientists. We need to know if we're going to a data scientist and say, okay, here is my data, and I don't know what I'm searching for, I don't think we will get any answer. Okay, we need to have a clear question and say how to best to be the most efficient to answer those questions.
Agreed. Yes, it's the way we work during the PhD. Any other?
I guess I could just ask, do we then lose discovery space, the unexpected?
Of course. It's a trade-off, okay? Well, okay, I'm working at IRAM, and IRAM is not producing so much data today, but because we are compressing in time, okay? So anything that would be time astronomy, today we would not be able to do it, okay? But if we were not doing this, we would, on the other hand, increase our data rate by a factor 10 to 100. And then we would need, we already are struggling to get the computer and the data center facility. So it's a question of trade-off on what you can do for which science, okay? And we are losing, maybe we are losing part of the science, okay? In part, this is the same. And at the LHC, for instance, they're filtering, it's even worse than SK, they're filtering their events to find the ones that they think that they are the most useful.
Yes, only start recording when the neutrino arrives. Any question? So the science should draw, the scientific question should draw the attention about, so which new science questions should appear in the near future? Because as Jerome says, those questions will draw the program and the observations and the way you track your data. Any idea?
So now let's try to bring back to ISM, because this is what we're doing here. In the radio window, as I said, there are key science questions and understanding, magnetic fields in the universe. It's a completely open question in terms of data observations. Okay, how do we constrain models of magnetic fields or amplifications in the universe? This is we don't know. We don't know how to bridge present models, right now we didn't have the data. We will have the data. So H1 will be a huge window in with the radio in the coming future. But then, of course, as Jerome was saying, I think what he was saying is just this is a huge facility that will handle, from stellar auroras to the cosmic web and epoch-ionization. So from cosmology to auroras in planets. Sorry, not solar. So the point is, every science project will have specific requirements, and the telescope will should be guided by these scientific questions that are very broad. So the specific needs will depend on the scientific questions behind, and it will be a trade-off, of course, eventually.
Yes, I think that one important thing is that will happen in the next decade is how do we generalize what we learn on the Milky Way for star formation and so on to Milky Way or nearby galaxy, let's say, to high redshift stuff. Where how do we and this is a question not only for science, it's a question for machine learning. Because on the Milky Way or a nearby galaxy, we have the resolutions and the sensitivity to get high detailed studies, but it's only a limited amount of space that we're studying. So let's say that we are training machine learning algorithms on the nearby universe. Can we generalize this to the high redshift universe? And this is a huge question. Can we, for instance, use physics informed machine learning in order to be able to generalize it to other environments that have not been studied?
That's an excellent question. So the generalization to new domains, so it's called domain transfer, is currently a very active research area in data science. And physics-informed learning is also a very active area. I think the combination of the two can give very promising results. But it's still at its beginning. So there is definitely scope for really good research, good multidisciplinary research here, and very good partnership with data scientists. That would be really interesting in both fields. There would be interesting science to be done in both fields. So it's definitely worth investigating.
So how can they convince data scientists to join? Maybe that's the
Well,
question.
with this kind of question, you already have a good argument because there's an open question in data science, which is not usually, which is not a question that you find in other data, in other fields like, well, you can find some of this data transfer question in, say, medical imaging or other fields, but with slightly different, with quite different parameters. Because in your case, when you change redshift, you don't just change resolution, you change your spectrum, you change whatever you are able to measure it will look different, and that's different from another imaging field. So you have some interesting challenges for data scientists, and that's a good argument to get data scientists interested.
Mark wanted to. No. Yes. Yes, like Frederic also asked a question on maybe. But you can do that. Any other question from the students? Like previously, one of the students asked about the AI teaching, where there are the black box, and how can this can be part of the curriculum or what did you think about the first week, about the teaching? Did it help to solve those kind of problems? You have people who are in between those two disciplinary, or was there still two black box? Any feedbacks on those, or
any inspiration you might have gained from last week to ask big questions for your field, or to learn more about your field? Something you would like to see in the next years?
Except for GPU training?
GPU training, I think we all need. Just so any last comments then from our panel for the future?
For young generations?
Well, one very specific thing about GPU training, just because people might not be aware of this, the large national computing centers in different countries often do offer courses like this, sometimes in person, sometimes online things. I know that's certainly the case in Germany. I think in the past it has definitely been the case in the UK. I don't know about other countries there, but there are courses available. So yeah, make use of that if that's something you want to learn about.
Thank you, Simon. It's time for coffee break?
Yes, I think that everyone would like coffee in their future.
Yes, probably.
So
thank you, everybody.
Thank you, everyone, and see you for the lecture afterwards.
Yes.